see them on the seminar website. So the link is given in the chat. Okay, so our second speaker is Subhajit Ghosh. He was still recently a PhD student at IISc with Arvind Iyer, and he has just joined a month ago as a postdoc at IIT Bombay. So it's a pleasure to have him. He will speak about the total variation cutoff, flip transpose top with random shuffle. Subhajit.
Okay, thank you, sir. And thanks to the organizer for giving me this opportunity to speak in this Bangalore probability seminar. Okay, so let me start. So I start with a brief overview of this presentation. So I start with a background and motivation for starting this model. Then I'll describe the flip transpose top with random shuffle. Then there will be some background, basic probability and representation theory to study this model as a random walk on a finite group, to be precise, the hyperoctahedral group. And then there will be some slides on computation of the spectrum of the transition matrix, and I'll study the mixing time for this shuffle. So we'll prove the cutoff phenomena. There will be some slides on that. And I end up with a biased variant of this shuffle and so about the cutoff phenomena for that model also. Okay. In general, the convergence rate related question for random walk on finite groups are useful in randomization algorithms. This has, or particularly mixing time of random walk on finite groups, has many applications in subjects including mathematics, computer science, statistical physics, and biology. So over the few decades, so many random walk model on finite groups has been studied. For example, random walk on n cycles, random walk on hypercube, and also the card shuffling models, which can be considered as random walk on the symmetric group. So the random walk on finite group receives its own independence, own problems and techniques from 1981, when Diaconis and Sasahani introduced the use of non-commutative Fourier analysis techniques in their work Random Transposition Model. They have proved cutoff phenomena for that. I'll define every terminology precisely in upcoming slides. Okay, so this particular model is mainly inspired by the transpose top with random shuffle, which was studied by Flatto, Oldesco, and Wells in 1985, and Diaconis proved the cutoff phenomena, total variation cutoff phenomena for this shuffle in 1987. Let me quickly mention what this shuffle is. Suppose we have a deck of n cards. So the shuffling scheme is the following. So we choose a card uniformly at random from the deck and transpose it with the top card. By transposing, I mean just interchanging. Okay, so here I am now going to explain our shuffling model, which is the flip transpose top with random shuffle. So suppose now we have n distinct cards and each card has two orientations. For the time being, one can think of the face of the cards have different colors. So we have n many distinct cards. And instead of looking at a deck of cards, we can explain it as the arrangement of cards in a particular row. This is the same thing. Okay, so the shuffling scheme is the following. Suppose we start from an arrangement of n distinct oriented cards in a row. Then the shuffling scheme is the following. So first choose a card uniformly at random from the row and transpose it with the last card after a random decision of flipping both the cards or not. So let's look at an example. So suppose we have a 9 distinct oriented cards. The orientations are presented in this picture by two different colors, blue and green. And suppose we have chose the 7th card. Then this shuffle essentially says that either we interchange the 7th and 9th position, which is this one, or we interchange the 7th and 9th position after flipping both of these. So by flipping, I mean changing the orientation of that particular card, and in this case that changes the color. So you can see that here 9 and 7 are interchanged and their colors also interchanged. I mean, yes, flipped. The cards are flipped. Okay. So this particular shuffle, we formulate it. Actually, this is a random walk on the hyperoctahedral group. So we formulate it in the upcoming slides as a random walk model on the hyperoctahedral group, which we denote by Bn. and our aim is to study the mixing time for this shuffle. I'll give precise definition in upcoming slides for the mixing time and all these things. Okay, so let me briefly recall what the hyperoctahedral group is. So a sign permutation, which is a bijection from the set plus minus 1 through up to plus minus n, such that it sends minus I to minus of pi I. For example, if pi is the sign permutation, that will be bijection from the set plus minus 1 through plus minus n, and which satisfies the condition pi of minus I equal to minus phi I for all I from 1 through n. This condition essentially says that if we know its value at the set 1 through n, then we can determine this bijection entirely. And this essentially gives this representation of a sign permutation, which we call in window notation. So pi subscript 1 is nothing but the image of pi under 1. So once we have this, now we can think of how to relate arrangement of n distinct oriented cards with uh, arrangement of our sign permutations. Okay, and huh?
Simple. Is it not same as Sn cross product with the two element group?
No, this is same as Sn wreath product with a two element group. You can think of a cyclic group of order 2 and take the semi, let's say Z2, and that is same as saying the semi-direct product of Z to the power n with Sn.
Okay.
Okay. So this particular sign permutations forms a group under the composition of permutation and or composition of mapping, which is known as the hyperoctahedral group, and which you denote using the notation Dn. Okay. So here is the connection between the arrangement of oriented uh, cards and the sign permutations. So suppose we choose this particular sign permutation pi 1, pi 2 up to pi n. This represent the arrangement of oriented cards in the following way. The label of the ith card will be mod of pi I, and its orientation is determined from the sign of pi I. If phi I is positive, we can think of, okay, this is blue orientation, or if it's negative, we can think of its green orientation. And again, I repeat, by flipping, orientation of a card can be changed. Okay. So yes, this is the thing. Every element or every arrangement of oriented cards in a row can be presented as a sign permutation in its window notation. Okay. So here comes some preliminary things from Markov chain. So throughout our presentation, I'll be restricting myself to discrete time Markov chain on finite state space, and I'll assume the chain is irreducible and aperiodic. Capital pi is the stationary distribution, and this is the known result that for irreducible aperiodic chain, no matter what the initial distribution is, your chain converges to the stationarity as the number of transition goes to infinity. Okay, so now given two probability measures mu and nu on omega, the total variation distance between them is defined to be the supremum over all subset A of omega of the difference between mu A and nu A. Particularly when omega is a finite set or a countable set, then this total variation distance can be think of half of the L1 distance between these two measures. The epsilon mixing time, we choose epsilon between 0 and 1 because total variation distance between any two measure is always bounded above by 1. So it's defined as follows. So we denote it by T mix epsilon, and it's the minimum of all those T for which D of T drops below the tolerance level epsilon, where D of T is the maximized total variation distance between the distribution after T many transition from the stationary distribution, and the maximum is taken over all the initial states. Okay. Now here comes a wonderful some sequence of finite Markov chain or Markov chain satisfies a wonderful property which is known as cutoff phenomena. Let me define what is that. So suppose we have a sequence of Markov chains and T mix n epsilon, this is the mixing time of the nth chain. Then we say that this sequence satisfy cutoff phenomena if these two condition holds. Particularly, this essentially says that if you look at large enough n, the mixing time of the NH chain doesn't depend on the tolerance level epsilon. This condition essentially says that. So let's look at it in a pictorial presentation or in a picture. Okay, so suppose for large enough n, we look at the graph of t versus dn of t. Dn is the total variation distance for the nth chain from the distribution after t minute transition from the stationary t. And here this blue line curve represents the plot of dnt versus t. So having cutoff phenomena, this says that the dnt is initially close to 1 and suddenly it drops off to very small value and then decays exponentially fast. So for cutoff phenomena, it says that if you increase your n, then this blue curve change in such a way that these two green line will come closer and closer, and that point will provide us the mixing time t mix epsilon, we can say, and we will say that that is the cutoff for this chain. Okay. Okay, I guess this explanation is clear what cutoff is. That's an important property for a sequence of Markov chain. Okay. Uh, okay, here comes some. Okay, so that was the probabilistic background. Here comes some representation theoretic background. So all this background theory I will use in posing our problem as random walk on the hyperoctahedral group. Okay. So by linear representation, I mean a homomorphism from the finite group G to GLV, where V is a finite dimensional vector space and GLV is the set of all invertible linear maps from V to itself. We can think of GLV as invertible matrices of size dimension V by dimension V. The vector space V is called an G module in this case, and also the dimension of the space V is defined to be the dimension of the representation rho. Particularly, if we choose our V to be this vector space CG. CG is nothing but the group algebra of G. This can be thought of as the vector space with over the field of complex number with basis G. And by means vector space, I am considering all formal linear combinations of G with coefficients from C. Okay. So then for this particular choice of V, if we look at the representation which sends a group element G to this particular element of GLCG, which sends an element of CG to another element of CG obtained by multiplying G on the right, is defined to be the right regular representation. Okay. So again, we call this rho to be irreducible if there doesn't exist a non-trivial proper subspace W of V which is stable under the action of rho, or in particular which is invariant under rho G for all G. So I should say that rho G we can think of an matrix, invertible matrix. Okay. And the set of all irreducible representation of G, we denote it using the notation G hat. Particularly this CG, this group algebra can be decomposed into irreducible G modules as follows, such that every irreducible G module come with multiplicity equal to their respective dimension. So this particular property I will use in proving the spectrum of the transition matrix. Okay. Here comes some more non-commutative Fourier analysis techniques. So given two probability measures P and Q on the finite group G, the convolution between them is denoted by P star QX, and it's defined to be the sum of all group elements Y of Px inverse times Qy. And the Fourier transformation of P at a representation rho is denoted by P hat rho, and it's defined to be the sum of over all group elements X of Px times rho X. So I should mention that rho X is a matrix since rho is an representation. So Px times rho X will be a matrix, and this essentially implies P hat rho will be a matrix. Okay. So by a random walk on the finite group G driven by P, we mean a Markov chain with state space G, and the transition probabilities given by one step transition probabilities are given by the chain will visit y in one transition from x with probability p of x inverse y, where x and y are states from the group G. Particularly, we can see that the transition probability matrix is nothing but the transpose of the Fourier transformation of the measure P at the right regular representation R. Okay. So particularly distribution after k many transitions will be given by P star k, where P star k is the k-fold convolution of P with itself. More precisely, this follows starting at x, the walk will visit y in k many transitions with probability P star k x inverse y. And it can be proved that this random walk on a finite group G driven by a probability measure P is irreducible if and only if the support of P generates the group G, and in that case the stationary distribution will be the uniform distribution on G. Okay, so here we have all the preliminary things to pose our model as random walk on the hyperoctahedral group. So now recall our shuffling scheme here. Then the flip transpose top with random shuffle on Bn is a random walk on Bn. Bn is the hyperoctahedral group driven by the probability measure P, where P is defined on Bn as follows. It's 1 by 2n if pi is identity. If pi is in, this essentially says that if you choose your I to be in between 0 and n minus 1, you just interchange the ith and nth cut, that with probability 1 over 2n. And this is again 1 over 2n is pi is minus in. This essentially says that we interchange the ith and nth card and flip both of them and 0 otherwise. So again, from this definition of P, we can see that P of pi equal to P of pi inverse. That immediately implies that the Fourier transformation of P at right regular representation, that matrix will be a symmetric matrix. Okay, so before going into that, it's let me mention that the support of P generates Bn. We can check that, and thus it is irreducible. And since this is a lazy chain, so it's aperiodic. The stationary distribution will be the uniform distribution, which we denote by UBN for this talk on Bn, and the transition matrix will be P hat R. We have removed the transpose sign, as I mentioned that P hat R in this case is a symmetric matrix. Okay, so our technique for obtaining the mixing time or studying the mixing time and looking at the cutoff phenomena are the spectral approach. So for that we need the eigenvalues of the transition matrix P hat R. So now I am going to explain how we obtain the what are the eigenvalues of the transition matrix for this shuffle. Okay, so here are some combinatorial definitions. So by a partition, we mean a sequence of weakly decreasing positive integers such that their sum is a particular positive integer n. So for a given positive integer n, we denote lambda to be a partition of n using this notation. Given any partition of a positive integer, we can visualize it as an arrangement of boxes such that the boxes are arranged in an left justified ways, and the ith row contains lambda I many boxes. Particularly, the examples for Young diagrams of the partitions of 4 are given by this example. One thing, one combinatorial object I just want to mention at this point is that suppose we have an Young diagram of a particular shape lambda, then we have where lambda is a partition of n, of course. So then we have n empty boxes. So suppose we have the numbers 1 through up to n, then we can fill the if we fill the numbers 1 through up to n inside the boxes, the combinatorial object we obtained is known as the Young tableau. And particularly, if an Young tableau is such that the entries in each row and each columns are increasing, then we call it a standard Young tableau of shape lambda. Okay, so now instead of having one Young diagram, suppose we have a pair of Young diagram. So let me define that. So a Young double diagram with n boxes is nothing but a ordered pair of Young diagrams such that the total number of boxes is n, and we denote this set using the notation this dn. So now given a Young double diagram with n boxes, we can again fill the numbers 1 through n in the empty boxes and obtain a pair of uh, tableau. Now, if the tableaus are in particular, each of the tableau are standard. That means each of the tableau, if you look at, the numbers are increasing along each row and each column, then we call it a standard Young double tableau, and definitely of a particular shape, where shape we denote is using notation mu, which is nothing but a pair of uh, Young diagrams. Okay. So, and tab D and mu is the set of all standard Young double tableau of shape mu. So here is an example of a standard Young double tableau of shape. The shape is corresponding to a pair of or corresponding to the double diagram with 8 many boxes in this case, where the first component is the partition 3 2 and the second component is the partition 2 1. Okay, so this is a particular example of a standard double tableau of shape mu. Now, given a Young diagram, we can locate its boxes or index its boxes using where it's situated. Suppose we are looking at a box which is situated at ith row and jth column, or maybe I should say xth row and yth column, because here is one I. So the box situated at xth row and yth column, its content is defined to be y minus x. Particularly for a Young double tableau or standard Young double tableau T, uh, we denote dt of I to represent the box inside T which contains I, and cbt of I to represent the content of that particular box. Okay, so here comes the main theorem on the spectrum of the transition matrix.
Can you just
Huh.
go back to the previous slide? I got
Yes. Yes.
double tableau means two tableau of same shape, right?
No, not same shape.
Oh, I see.
They can be of any shape, but the total number of boxes. So the first component may be a partition of M1, second component may be partition of M2, such that M1 plus M2 is N. That's the thing.
Oh. Okay, thanks.
Okay. Okay, so here is the theorem on the spectrum. So for any Young double diagram mu inside Dn, so I could think of mu as mu superscript 1, mu superscript 2, where mu superscript 1 is a Young diagram, mu superscript 2 is also a Young diagram, which satisfies that mu1 is a partition of M, then definitely mu2 will definitely be a partition of n minus m, where m is between this set 0 1 through up to floor of n by 2. And for this choice of mu, we for every t inside this tab d n mu, this cbtn plus 1 over n and cbtn over n are eigenvalues of the transition matrix with multiplicity m mu, where m mu is given by this. If m is, so this is for when m is odd, and when m is even, m mu is half of this n choose m d mu1 d mu2. Okay, so I should mention what is d mu1 and d mu2. So d mu1 is the number of standard Young tableau of shape mu1. And so, okay, let's look at an example to understand this theorem. So suppose we are setting our n to be 2. We are looking at on flip transpose top with random shuffle with 2 oriented cards. Then, so the eigenvalues are this given by this, and these are the elements of I should say tab D2 for mu. So let me explain for a particular mu. Suppose we have chosen this particular mu. So this is where mu is, the first component is the empty diagram and the second component is corresponding to the partition 1 1. Then the only choice of the standard Young double tableau of this shape is this particular one, phi and 1 2. That's the only choice. Then the eigenvalue corresponding to this t. So for this particular t, the eigenvalues will be these two, 0 and minus of y, because we have to look at 2. Here n is 2. So it's situated at this position, and the content of this box is minus 1, because this is on the first column, second row. So its content is minus 1. So the eigenvalues will be -1 plus 1 over 2, that is 0, and -1 over 2, that is minus half. And its multiplicity will be given by m of this particular shape phi and these empty boxes 1 1. For that, n is 2 and m is 0 because size of phi is 0. So and d mu 1 is obviously 1. We assume that there is a unique Young diagram of shape empty shape, and that definitely implies unique Young diagram, or I mean unique standard Young tableau of empty shape. And d mu 2 is obviously 1 because, as I mentioned, that only one choice of we have only one choice of filling these boxes. So this mu for this particular choice of mu will be 1. So 0 and minus half will come with multiplicity 1. So other I'm not going to explain now. The similarly we can obtain. Okay, so the proof, basically the proof techniques is we follow the representation theory of the hyperoctahedral group Bn, and basically we obtain the eigenvalues of p hat r when we restrict it to irreducible Bn modules. That's where we use the decomposition of that C of Bn, the group algebra C of Bn. And particularly I should say that proof techniques follows the Varsi-Koven-Cook theory for the representation theory of Bn. So I'm going to skip the proof techniques because I still have some slides to present, and I guess I am running out of time. So maybe I'm skipping this particular slide on the proof techniques. Okay, so now directly I jump to the obtaining the upper bound of the total variation distance between P star K and the stationary distribution. So once we have the eigenvalues, we use the celebrated Diaconis-Sassani lemma, which says that for random walk on a finite group G, the total variation distance between the distribution after k-many transition and the stationary distribution is bounded above by the 2kth power of the eigenvalues of the, I should maybe, okay, I should just replace it in the following way. So 4 times the square of the total variation distance, uh, 4 times the square of the total variation distance between P star K and the stationary distribution is bounded above by the 2kth power of the eigenvalues of the transition matrix, except the largest eigenvalue, which will be 1. So once we have the result on the eigenvalues of the transition matrix, we can use that lemma. And after writing down the eigenvalues in the lemma, in the formula, we have this particular upper bound. So in particular, there are 3 expressions in the right hand side. If we look at the third expression, then for k greater or equal to n log n, that third expression can be bounded above by this quantity 4e times e power n square times e power minus 2k over n minus 1. And the second expression can be bounded above by this particular quantity. Here we do not have any condition on k. Thus 4 times the total variation distance between P star K and UBN square is bounded above by this quantity, and that is for all K greater or equal to n log n because of this. So once we have this, we just plug in the value of K equal to, let me go back to my earlier slide for the statement of the theorem. So once we have that particular inequality, we plug in the value of K equal to n log n plus Cn in that to obtain this upper bound. So it's enough to plug in k equal to n log n plus Cn, because as k increases, this quantity will get smaller and smaller.
One question.
Yes, sir.
Previous slide, that n minus 1 by n, that second largest eigenvalue.
Yes.
It is which one in your theorem on eigenvalues? Which mu1, mu2, or whatever that was?
Yes. So actually, the second largest eigenvalue will come from many irreducibles. So here I have written it in particular for the case where your first component is empty, I mean phi, and the second component is 1 power n. The just only one column of boxes.
So
but you have many irreducible representations. So the second largest eigenvalue will have multiplicity more than 1.
So, but then that should multiply this, right? It makes no difference, but it should come with the multiplicity, isn't it?
No, no. I have written it in terms of the following. So eigenvalues I have written in the following way with the multiplicities. So particularly this one I have written for a particular choice of Young double diagram, which is corresponding to phi and 1 power n, because you can see that these are corresponding to, so I have to exclude one particular thing which is the largest and which will come from the trivial trivial I should say, maybe, huh?
Yes.
So because the first component will be a partition of n and the second component will be empty.
Okay.
So then, so okay, so in the, if you look at the proof, so I runs my m through 0 to up to floor of n by 2. So every time I choose an m, I am taking care of two particular things. One is m comma n minus n m, and the other is n minus m comma m. That's corresponds to these two choices. Okay.
Okay.
So this particular choice is coming from, so if you have something like m, a single row and the empty, that will give you the eigenvalue 1, which we will not consider. Similarly, that if you just flip the order, I mean you have the something phi, again you flip the order, that will also give you another thing, another permutation. That is why sorry, another eigenvalue. So this particular is coming from that thing. So if you look at phi and oh sorry, this particular is coming from phi and n.
Phi and n. Okay.
Sorry, that should come from phi and n, not 1 to the power n, sorry.
Okay.
Maybe at the end I will come to that and explain it more clearly. Okay. Okay, so now here is the rough sketch of the proof of this upper bound theorem. So now I come to the lower bound. So for the lower bound, I use the argument on lumping of Markov chains. Okay. So first define a surjective homomorphism from the hyperoctahedral group Bn to the symmetric group Sn as follows. So take an element of Bn, which we send it to a permutation. Just we can think of, we have an arrangement of oriented cards. We just forget about the orientations and just only labeling are there. That will give our this map F. So under this map F, the flip transpose top with random shuffle on Bn projects to the transpose top with random shuffle on Sn. And also, if Q is the generator of the transpose top with random shuffle on Sn, then we can check that P of F inverse is Q. And also we can prove that P of F inverse, the convolution of P of F inverse K times with itself is same as P star K F inverse. This proof we followed induction, we proved this using induction on K. And we also have U Bn F star F inverse equal to U Sn. Okay, so now here is the main punchline for considering this transpose top with random shuffle on Sn. So this essentially says that the total variation distance for the uh, original chain is greater than equal to that for the lumped chain. And this follows from this particular result, which says that if you for any two distribution mu1 nu1 omega, and for a map psi, total variation distance between mu and nu is at least mu psi inverse, at least the total variation distance between mu psi inverse and nu psi inverse, with the underlying assumption that lambda is finite. So for this our particular case, psi is f, this omega is bn, lambda is sn, and mu is p star k, and nu is ubn. Okay, so once we have this, we recall the result of Diaconis, who for the transpose top with random shuffle on Sn. He has proved that this total variation distance between q star k and the uniform distribution on Sn is bounded below by this big expression for k greater than 1. Once we have this, we can say immediately that the total variation distance between, for our case, is bounded below by the same quantity. And now if you plug in your k equal to n log n plus cn, where c is a negative number, then we have this inequality result, which provides us the lower bound for this total variation distance. Particularly, I should mention that if you tend your C to minus infinity, you can see that this right hand side is going to 1. So that essentially says that the limit of this as C tends to minus infinity is 1. Okay. So here is the final result on cutoff. So looking at the upper bound, we can choose a particular C1 such that this quantity can be made less than epsilon. That is immediately implies that we have a choice of positive integer n naught such that for all n greater equal to n naught, we have this side of the inequality. Again, if we look at, okay, so we can, the choice of the such C1 ensures by, if you take your this C to infinity, then this quantity can be made equal to 0. So similarly, if you take, as I mentioned, that if you take for the lower bound case, your C tend to minus infinity, this quantity, the lower bound can go to 1. That immediately implies that we have a choice of C naught, which is negative, for which n log n plus C naught n is less than equal to the epsilon mixing time for the nth chain. So as we are looking at the case of n card, I am writing this as T mix n epsilon. Okay, so once we have this divided throughout by n log n and take limit as n tends to infinity, this immediately implies the existence of cutoff for our chain at n log n. Okay, so for final few minutes, I'll explain a biased variant for this shuffle. So what it says first, suppose we choose an number between 0 and 1, alpha, and we consider the following shuffle. So with probability alpha, we do the same thing what we did for the flip transpose top with random shuffle on Bn. And with probability 1 minus alpha, we do the following. So we just choose a card uniformly at random and just transpose it with the top card after a random division of flipping one of the card. So for example, you choose the ith card, you interchange the nth card and ith card and flip the, after interchange, you flip the card on your left hand, or maybe the card at the ith position, or maybe you can just interchange only the nth card without interchanging the card on the ith position. Just one interchange will, I mean, not interchange, sorry, just one flip will be there. For the flip transpose, we did something that after interchanging or after transposing, we were either flipping both the cards or not. But for this case, we do that with probability alpha, and with probability 1 minus alpha, we just after interchanging, we flip one of the cards, not both the cards. Or maybe we can do, I mean, we also allow, we not flip any of the card. That is also allowed for the probability 1 minus alpha case. Okay. So particularly, if you set your alpha equal to 1, then it boils down to the flip transpose top with random shuffle on Bn. So it can be seen that this biased variant is a random walk on Bn driven by the probability measure P alpha, where P alpha pi is defined as here. So it's this essentially says that if you interchange the ith and nth card, and you interchange the ith and nth card and flip both of them, this particular essentially says that you interchange the ith and nth card and then you interchange the nth card, and this essentially says that you interchange the ith and nth card and then you flip the ith card. Okay, so here is the theorem on the spectrum of the transition matrix for the biased variant. So the techniques for proving the spectrum, proving the theorem on the spectrum is same as what we used for the case of unbiased variant. So, and you can also see that the eigenvalues are same, and for some eigenvalues are same, and some eigenvalues are the eigenvalues of the unbiased chain multiplied with this factor 2 alpha minus 1. So for that alpha, we have this 2 alpha minus 1 is strictly between minus 1 and 1. So that immediately implies the absolute value of the eigenvalues of the biased variant are bounded above by the corresponding eigenvalues of the unbiased variant. So once we have this result, so we can say that this total upper bound for the total variation distance between the unbiased chain and the biased chain are same. Again, using the same map what we used for the unbiased variant, if we can see that this biased chain also projects to the uh, transpose top with random shuffle on Sn, and therefore the lower bound for the unbiased chain and the biased chain will be same. So once we have the same upper bound and lower bound, we can easily see that the cutoff for the biased variant at n log n. Okay, so here are some references, and thank you.
Okay. So, any questions, comments to Subhajit?
One question.
Yes.
What's the motivation for considering these oriented cards? I mean, it's very nice and mathematically, but is there any other?
Yeah, only the mathematical motivation I can say, and the other thing is that uh, in general, if we see, the state space size has become doubled. So I mean, no, not state space size. So there we had n cards, but here we are dealing with something with 2n things, because each has two orientations and we have n cards. So in general, I mean, it's completely mathematical motivation. So the cutoff, if it would have exist before considering this model, that might be something between n log n and 2n log 2n. So to prove that it's the correct order is n log n, that was, I mean, yeah, so that was the something nice, I feel. That's
Okay.
all.
Okay, that's okay. Nice.
This biased one you said is more mixing faster than the other one, right? I mean, so is that
No, it's mixing with the same order, na? Because
order right? But I mean, it is in a way you are doing a bit more, right? So you are allowing one of them to flip, but not the other.
yes, no, so that is also with some probability, because so there what I was doing the flip thing with either interchanging with flipping both of them. Here I am doing that also with some particular probability, and with the remaining probability I am doing what you just told, that just flipping one of them.
Yes. Okay.
But yeah, that might happen that yes, before considering this, it would have happened that uh, the mixing time change, but it's nice that the mixing time is the same n log n.
Yeah, n log n is fine in all three cases, n log n. But the what is the constant in terms of in front of n? Probably you can figure it out exactly, right? In the three cases, you can write even lower order terms. You can write it as n log n minus constant n plus, I mean, even lower order terms. So the
Yes.
constant, that constant is different in the three cases. Is it or is it not the case?
Okay. Whatever depends on the tolerance level, does that change, you mean, right?
Yeah.
Okay.
Is it? Okay, I don't know if it should show up at that order, but that's the question. Yeah.
uh, Maybe for the bias chain it will mix faster, then I guess so, because I am doing something more here, as you mentioned.
Yeah. But even with the original, I don't know whether compared to the just top to random and that, whether the factor in front of n is different.
Factor in front of n, n means you are talking about the leading order, or the remaining thing.
At C naught and C1 n that you have written.
Yes.
Out the exact constant in front of n, right? So that
Yes. Probably for the unbiased variant, that this mix, the oriented version mixes fast for the non-oriented version.
Why?
That's my guess.
No, the non-oriented one should mix fast, right? Because you had the projection after all.
Oh, sorry. Yes.
Okay.
That's the thing I have used in the lower bound case. Sorry.
Yeah, that's what I meant. Yeah. Okay.
Uh-huh. And sir, should I go to that eigenvalue theorem? That time I just mixed up something.
My
So
only question was, no, you answered my question. So that comes with multiplicity 1. Is that correct?
no. Second largest eigenvalue will come with multiplicity more than 1. Actually, that makes the
But why did you not write that? Is my confusion.
okay. So I have not written with the multiplicity that way. So see, so if you look at this eigenvalue thing, okay, so just so mu is the multiplicity for each of these my eigenvalue. So I have written here just blindly, I just follow this eigenvalue theorem and written this quantity, but here I skip m equal to 0 case, right? But I should start from m equal to 0. So this part will take care of the case m equal to 0. So now again, m equal to 0 means what? I should look at a pair of Young diagrams such that the first component will give me a partition of 0 and the second component will give me a partition of n, right?
Okay.
So particularly the first the and that should give me something, these two different eigenvalues. But if you look at these two different eigenvalues, the first component is corresponding to 0, then you have the eigenvalues like one eigenvalue will be 1 and the other, so we have phi and n, or 0 and n. So we looked at empty diagram on the left component and all possible partitions on the right component, right? So that corresponds to this particular these two things. So these two things are for m equal to 0. So you can
Let me ask. I'm asking probably something simpler than what you're trying to say. This is so. What is the Diaconis-Shashani theorem that left side quantity is equal to sum of the 2k powers of all the eigenvalues?
yes, except the largest one.
Except the largest one. Okay, largest one is 1. It is left.
1. Yes.
Now, but in the next slide, you bounded the second summand and the third summand. Both are lower order than the first one. Is that not right?
Both of the second third summand and the second summand,
They are negligible compared to the first one. Is that correct or not?
no, they are not negligible. See, because what is the first one? First one is the 1 minus 1 over n to the power 2k. That can be bounded above by this quantity e power minus 2k by n.
Okay.
So this quantity is much more negligible than this one. So these have the much more contributions here.
Okay. So
and that essentially implies that you will have, so this is the definitely this is the second largest eigenvalue, but we will have also second largest eigenvalue inside this. We are not taking care about the multiplicity separately. Whatever eigenvalue we'll have distinct, we just write down in the 2k power.
I see.
So multiplicity will be automatically taken care of these two things.
I see. Okay. Fine. Okay. So are there any other questions? So if anyone else has, let's take that. Yes. Okay. So if not, maybe everyone can unmute themselves and we can thank Subhajit. So. Okay.